Hi guys, so here we are at 14.3 ideal gases, and let me just start out by saying this isn't how I thought this year would end, and I really miss you, and please stop by and see me. So, ideal gases. Real gases we see in every day do not behave the way that we calculate them with because it gets too complicated. However, under certain conditions, we can make these calculations and they are fairly accurate, but those conditions have to be met. So, how can you blanket a stage with fog? And we usually call these smoke machines, but they're not really smoke. They're actually carbon dioxide, and we made it into a solid by putting it under very high pressure, compressing a volume to very, very small, and we can convert a gas, carbon dioxide, into a solid. That solid is very, very cold, and it will go directly from the solid to the gas state, creating what looks like smoke or fog. And it's actually just the water vapor in the air gets cold because that solid carbon dioxide is very, very cold. And so it turns the water vapor in the air into very small particles, or basically fog or cloud. So you're really creating a cloud. So, how can you calculate the amount of contained gas when the pressure, volume, and temperature are specified? So, if I know 3 of 4 variables, I can calculate the fourth. And so I need to know pressure, volume, temperature, and I can calculate volume. If I know volume, pressure, or the amount. So if I know the amount of gas, etc., I can calculate the others. Suppose you want to calculate the number of moles of a gas in a fixed volume at a known temperature and pressure. The volume occupied by the gas at the specified temperature and the pressure depends on the number of particles. So, the number of moles of a gas is directly proportional to the number of particles. If I know the number of moles, I could calculate the particles. And moles must be directly proportional to the volume. And so we have an equation we're going to get to shortly. You can introduce moles into the combined gas law by dividing each side by the number of moles, since we just said how they're related. And so the equation we would get is P1 times V1 over T1 times N1. And that would be equal to a constant. And that constant ends up being the ideal gas equation constant. And so we get this equation by dividing both sides by N. And then we can just say that the ideal gas constant R is equal to P times V over T times N. Or the way you're probably used to seeing it, since we know a real gas at STP, 0 Celsius, and 1 atmosphere is 22.4 liters. We can actually calculate out the volume, the constant for R. So if we put in at STP what R is, that constant can be calculated. And we typically don't do this in kilopascals, although they're doing it that way. I typically have you use ATM. So this is called the ideal gas law, and it's at PV equals nRT. And P is pressure, V is volume, N is the ideal gas constant, and R is the ideal gas law constant, N is the number of moles, and T is the temperature. And temperature, again, must be in Kelvin. It cannot be in Celsius, because then we would end up with a negative number for pressure, volume, or number of moles. So when pressure, volume, and temperature of a contained gas are known, we can use the ideal gas law to calculate the number of moles. At 34 Celsius, the pressure inside a nitrogen-filled tennis ball with a volume of 0.148 liters is 212 kilopascals. How many moles of nitrogen gas are in the ball? So we know the pressure, we know the volume, we know the temperature, and we know the ideal gas law constant. and we want to know the number of moles. The first thing I would do here is convert temperature into Celsius by adding 273 to it. And then you substitute, I would rearrange this equation solving for N, so I would have PV divided by RT. And now I'm ready to substitute into my equation the values and making sure that all my units cancel. And I would get that it's 1.23 times 10 to the negative 2 moles of nitrogen. Tennis ball has a small volume and is not under a great deal of pressure. Is it reasonable that it contains a small amount of nitrogen gas? And the answer to that is probably yes. Because remember, at STP, 1 liter or 1 mole of gas is 22.4 liters. That volume was really small comparatively. So, deep underground, a cavern contains 2.24 times 10 to the 6 liters of methane gas at a pressure of 1.50 times 10 to the third kilopascals. And the temperature of 315 Kelvin. How many kilograms of methane does the cavern contain? So this isn't asking for moles, but if I find moles, then I can calculate how many kilograms. By using molar mass, I can go to grams and then convert grams to kilograms. So in my head, I've already figured out that I'm going to use the ideal gas law to get moles, then I'm going to use molar mass to get grams, and then I'll convert to kilograms. So kind of a 3-step process. So we have our pressure, our volume, our temperature. We know what R is. We can calculate the molar mass of methane, and that will give us a mass of methane. So N is going to equal PV over RT. Substitute in, we get that we have 1.28 times 10 to the 6 moles of methane. Once I have my moles of methane, I can use my molar mass to get grams of methane, and then I can convert from grams to kilograms by using that there are 1 times 10 to the third grams of anything in 1 kilogram. So, although it's very compressed, the volume is still very large, so it is reasonable that it contains a large amount of methane. So how would you rearrange the ideal gas law to isolate temperature? So remember, PV equals nRT. So looking at this, I know P and V have to be together, so it's either A or C. And since temperature times RT equals PV, I think it's going to be C. There we go. So, under what conditions are real gases most likely to differ from ideal gases? So, an ideal gas is one where the gas law, pressure and temperature are two constraints. So particles could have no volume. The particles could what we want ideal gases, or what we assume about them, is that the particles of the gas have no volume and that there's no attraction between particles, because if there was an attraction between particles, they would form a liquid or a solid. So there's no gas for which these assumptions are always true. So an ideal gas actually does not exist. We still use it, and it's still helpful. At many conditions of temperature and pressure, a real gas behaves much like an ideal gas. And what are those conditions? The particles of real gas have volume, and the particles have attraction between them. Because of these attractions, a gas can condense or even liquefy when it is compressed or cooled. And so the gentleman there is actually working with, I believe, liquid nitrogen. Real gases differ most from ideal gases at low temperatures and at high pressures. So if I get much below 0 Celsius or much above, several times the atmospheric pressure, that's when they start to deviate from real gases. So, what are the characteristics of a real ideal gas? The particles of an ideal gas have no volume and there is no attraction between them. Certain types of fog machines use dry ice and water to create stage fog. What phase change occurs when stage fog is made? And that's the dry ice doesn't melt, but it actually sublimes. It goes from the solid to the gas without going through the liquid. And the water vapor in the air condenses to form white fog. So, here we are at the end. When the pressure and volume and temperature of a contained gas are known, you can use the ideal gas law to calculate the number of moles. Real gases differ from most ideal gases at low temperature and high pressure, and the ideal gas equation is PV equals nRT. Ideal gas constant is 8.31 liters kilopascals per mole Kelvin. The ideal gas law equation again. Kinetic molecular theory, I would definitely make sure that you pause the video here and write these down if you don't have them in your notes already. Hint, I bet that'll be on the quiz. And here we are at the end of this. And this is actually exactly where I expected to end this year. And I have to say, you guys have been real troopers and you've worked really hard, and I appreciate your efforts. Don't forget, we have a quiz online, and then we will meet Thursday in Teams. Thanks again. Hope to see you soon.